Hello, everyone. This is the pre-recorded lecture for week 5 of Education 6050, the Applied Statistical Analysis course. So today we're going to be talking about hypothesis testing with z-scores briefly, and then we're going to introduce the more common t-tests. We're going to do one sample, independent samples, and paired samples. So these tests, you can look at it when you're going to actually be able to use these. So for the z-test, that's a single group. You just have one group, and you know the population mean and standard deviation. So you know the population that you're comparing to, its mean and standard deviation. And you're just going to bring in a group and see if they're different from that population. For one sample t-test, you're going to take in a single group. But this time, you know the population mean, but not the standard deviation. For independent samples t-test, that's when you have now two groups. So with a z-test and a one sample t-test, you just have one group. You don't have anyone experiencing anything different than the others. They're all just experiencing the same thing. So you could just bring people in and give them an intervention and compare them to some known population. That would be single group. So that would be a z-test or a one sample, depending on what you know about the population. But a lot more common, we're going to have either two independent groups, which is the independent samples T, or we're going to bring in the same individuals measured two or more times, or match them up based on some characteristics. In those situations, when you have two independent groups, that means you bring in one group of people, they receive some sort of intervention, and then you bring in another group of people, and maybe you give them a placebo, so they think they get the intervention, but they actually don't. When it comes to the paired samples or dependent samples, all the same, the situation is you bring people in, give them some sort of situation, and then you bring them in again another time. So you see these a lot with like pre-post-test designs where you test them, do something, and then test them again. So you can get a feel for what these look like and how they compare and how they differ from each other. We're going to go through each one. With the z-test, we've already talked a bit about that, so we're just going to review. And then we're going to jump into the one sample T. From there, we'll go to independent samples and then paired samples. So first, z-scores for an individual point. This is a very unique, it's not the z-test. We're just looking at a single point. So X is just a single person. This is the mean of the sample and the standard deviation. And this tells us if the score is above or below the mean and how large, in other words, the magnitude, the deviation from the mean is to other data points. So that's a z-score. When we talk about z-scores, that's almost always what we're talking about. When it comes to a z-test, this is when we're actually comparing the mean of a sample. So we're comparing a whole group of people to a known population mean, and we divide it by the standard error of the mean. So if you remember, the standard error of the mean is sigma over the square root of n. So when we're doing a z-test, we're comparing a whole sample to something we know about the population already. For a z-score, it's just a single individual in a sample compared to the rest of that sample. And again, with the z-score, you have the standard normal curve, so you have the 68, 95, and 99.7 rule that we talked about. But all this assumes that we know the population mean and standard deviation. So what if we don't know the population standard deviation, or sigma? We then can use a one sample t-test. It's just like the z-test, but we're going to estimate the sigma, the standard deviation, instead of using what we already know. And because we're just estimating this, we use a slightly different table for the p-values. It's going to be very similar to the standard normal, but it's going to be slightly different. Because it's way more common, we're just going to show an example of the one sample t-test instead of the z-test. Almost always you're going to use the one sample t instead of a z. So the one sample t-test, just like the z, we're comparing the mean of our sample to some known population mean, and we're dividing by the SEM. But this time, instead of sigma, we're using our sample standard deviation instead of the population standard deviation. So just as review, one sample t-test versus a z-test. This one you know the mean and standard deviation. This one you know the population mean, but not the standard deviation. The z-test results from this equation where you know sigma. The t-test results from this one where you're estimating sigma. But otherwise, they are essentially the same. So when it comes to single sample t-tests, the requirements are we need a dependent variable that is interval or ratio, so a continuous variable. The independent variable defines one sample, so we just have one group come in. And we don't know the population standard deviation. So this figure shows the comparison between the z distribution, the normal distribution, and what the t distribution looks like. It's much flatter and has bigger tails, just heavier tails. There's more stuff in the tails when you have a really small n. When your sample size gets bigger, say around 30, it starts to look more and more like the normal. And somewhere around 120 to 150, the t distribution and the z distribution look identical. So we're going to get p-values from this distribution just like we did with the z, but instead we're going to be using the t distribution. As before, we're going to use the 6-step approach to hypothesis testing. Number one is examine the variables to assess the assumptions. So our basic assumptions are independence of data, which means the individuals are independent of each other. They don't influence each other at all. In other words, all the people we bring in our sample, they aren't related in some way. They're not family members, they're not married, they're not friends, things like that. The appropriate measurement, in this case we need the interval ratio dependent variable and an IV that's essentially just a single sample, just a single group. We also need normality of our outcome, of the DV. It should be roughly normal. However, this is only really important for small samples, samples smaller than roughly 30. Then the last one is homogeneity of variance. That means our variance, so the variance of our sample is roughly the same size as the variance in the population. The question is, can we really know that? And there are ways that we can look at these basic assumptions. For independence, we can do a random sample that helps ensure independence. We need to know what our variables are to know if we have appropriate measurement. Normality, we can check histograms. We can look at the skew and kurtosis outputs from Jamovi. But when it comes to homogeneity of variance in the one sample t-test, it's really hard to assess. We don't know the population variance. All we know is what our sample looks like, and so we can't really compare it to anything. And other tests that we'll talk about in just a minute will have actually a test for that one, but in this case we don't. Here, when we state the null and research hypotheses, the null is always that our sample and the population are the same. But note, we are using mu here, the funky U-looking thing, instead of capital M because we're talking about the population that these represent. So in this case, we are comparing our class. So if we brought in our class to see if they are, let's say, more intelligent than the population, which I think you guys are, if we were testing that, we would get a sample, get an estimate of the population, class, whatever our class represents, that population, in this case, grad students and social science degrees. So we're estimating if we could grab that whole population, what their mean would be, and comparing that to this hypothesized mean of the population that we believe we know. And so the null hypothesis, when this is the case, that means there's no real difference between the class and the population. So of course, our class's mean is not going to be exactly the same as the population's mean. But our question is that difference real because there's a real difference out there, or is it just random chance? It's just sampling error. We just happens to be that way. They're just slightly different. And that's what we're trying to get at with the null and research hypotheses. So the research hypothesis is saying, yes, there is a difference. The class's mean is different than the population mean, and that is a true difference. There's a real difference out there in the world. When it comes to step 3, defining critical regions, we're trying to answer the question, how much evidence is enough to believe that the null is not true? In other words, before analyzing the data, we need to say, this is our line. There's critical regions. If we're out there, if we're that far away, then that is enough evidence for us to say, yeah, we think there's a lot of evidence saying that the null is not actually true. With a t-test, it's often going to be around here. So if the t that we calculate in the next step is over here or over here, or in other words, our p-value is less than 0.05, then we're going to reject the null and say it's not true. So importantly, we decide on an alpha first, and then we calculate the critical value. I'm going to show how that can be done with a table. But again, this is not going to be emphasized in this class. I just want to show you what it looks like if we're using the table. This is the t-distribution table. Across the side, we have what's called the degrees of freedom. I'll tell you what the degrees of freedom are for this test, and then the p-value. Because this table is based on a one-tail, for a two-tailed test, we just move over 1 to 0.025. So if our alpha is 0.05, we're going to actually use this column. So in this test, this is going to change based on what statistical test we use. Our degrees of freedom is n minus 1. So whatever our sample is, minus 1. So let's say we had a sample of 30. So our degrees of freedom would turn out to be 29. That means if our alpha was 0.05 and our degrees of freedom is 29, our critical t-value is 2.05 roughly. So if our observed t-statistic is bigger than that in the positive direction, or it's lower than that in the negative direction, so if it's, let's say, 3 or negative 3, then we would reject the null. On the exam, if you're writing what our critical regions are, we would just say something along the lines of alpha equals 0.05, and our critical t-value with 29 degrees of freedom is 2.05. The next step is actually calculating the t-statistic. Mostly we're going to use Jamovi to do this for us, but this is how it's defined, like we talked about before. In any case, if I'm having you calculate any of this, you would have the SEM, this part, the mu, and the m would be given to you. With that t, we can calculate it and compare it to the critical t, and if it's further away from 0 than the critical t, then it's significant. Or we can look at its p-value. In Jamovi, we're going to be given a p-value, and so that's what we're going to actually rely on most of the time. We're going to compare that to our alpha level. That is, if our p-value is, say, 0.03 and our alpha is 0.05, that means it's significant. We also will want to compute an effect size and describe it. One of the ones that comes up all the time is called Cohens D. It's a standardized mean difference score. It's the mean of our sample minus the mean of the population over the standard deviation. That's going to give us our D. And Cohen defined these as 0.2 being small, 0.5 being moderate, and 0.8 are large. This is not the case for every single field. You'll want to fill it out. What is a big effect in your field? What's a small effect? But these are kind of general ideas to get in mind of where things are at. The last step is interpreting the results. You want to put the results into words that someone outside of this class might understand. There's an example of it on page 216 in the book. You can use that as a template. There's going to be lots of other examples. And in the actual in-person part of the class, we're going to interpret everything we do in Jamovi, so there's going to be some practice with this. All right, that is one sample t-test. The next one is the independent samples t-test. With the one sample t-test, we just have a single sample, a single group, and we're comparing it to a known population. With the independent samples t-test, this is more common. We're actually bringing in two independent groups. So the groups don't have the same people, and they're not related in any way. We just bring them in, and the best way usually is just to randomly assign them to a group. So we have someone come in, we just randomly assign them to one of the groups. Let's say treatment and control. The treatment group will get some sort of intervention. The control group will get a placebo or something. For the one sample, this was the t-test calculation. For this one, it looks way worse. But if you keep in mind that our null hypothesis is going to be that the two groups do not differ, that means this is going to turn into 0. These are going to be the same. So this is totally going to drop out, this part. What we're left with is the mean of group 1 minus the mean of group 2 over what's called the pooled standard deviation divided by the square root of n. As before, we're still using the same t-distribution. Nothing's changed there. As for the requirements, we need a dependent variable that's on an interval ratio scale. In this case, our outcome, it looks continuous. It ranges from 9 to 5, it looks like. We have an independent variable that defines two different groups. In this case, we call it group, and it has 1s or 2s. And the groups are independent. They're not repeated measures. In other words, person number 1 had a score of 8, and they're in group 1, and you do not see individual 1 in group 2 as well. They're just in group 1. Same goes for, let's say, person number 7. They got a score of 5, and they're in group 2. You don't see them anywhere else in group 1. That is, each individual is only in one group and just measured with that specific outcome just once. Probably not a shocker. We're going to use the same 6-step approach with the independent samples t-test as we did with the one sample. With that, our Step one is looking at basic assumptions. These are roughly the same as before. Independence is the same. The groups are independent of each other, and each individual in the groups are independent of each other. The measurements are appropriate where we have an interval ratio dependent variable and an IV that defines two groups. Normality, same thing as before. And now homogeneity of variance, where the variances of the two groups should be equal. This time we actually can compare them because we have the two groups and we're going to compare, are their variances roughly the same? When they're not, there's ways around that, we can handle that, but ideally they're the same. When we want to check the assumptions, for independence we need to do a random sample. That is usually the best way to ensure independence. The appropriate measure, we need to know what our variables are, what they mean. Normality, we can look at histograms and skew and kurtosis from Jamovi. And then for homogeneity, in this case, and several others that we'll encounter, you can use Levine's test. This will actually do a formal test to compare the variances across the two groups and see if they're roughly the same. Here, now we have the same general idea of the null and research hypothesis, where the research says one of the group's means is different than the other. There is a difference. And then the null is there is no real difference between the group 1 and the group 2 means. So in this case, the population that group 1 represents is equal to the population that group 2 represents. Their means are the same. In our sample, even if our means are slightly different, that would just be due to random chance if the null hypothesis is true. It's just our groups had slight differences when they came in, and that's just what happened, so there's a little bit of differences there. If we go with the research hypothesis, we're saying that the difference that we're seeing in our sample is a real difference. And step 3 is basically identical. For most of the hypothesis testing that we go through, they're going to be very, very similar. We're just always asking, how big do these things need to differ, or how surprising does this result need to be when the null is true for us to start to think, okay, the null must not be true. So we're going to do the same stuff here. The thing that differs here is that we now have a degree of freedom. The degrees of freedom is n of our first group plus n of our second group minus 2. Let's say we had 15 in this group and 16 in this group. That would give us a degree, the degrees of freedom would be 29. Again, we would go over 0.025, and again, our critical would be 2.05. Our critical regions we could define as either alpha equals 0.05, or we could use our T critical, the cutoff point. Again, when we actually calculate this, Jamovi is going to give us a p-value, and we can just use that. Step 4, computing the test statistic. Our test statistic is going to be the independent samples T. If you remember, this drops out because our null is almost always that they are the same. So it's going to be the difference between the means divided by these things. Our Cohens D is now the mean of group 1 minus the mean of group 2 over the pooled standard deviation. Just slightly different than what we saw before. It's still a Cohens D. And the rough designations are still the same. Again, step 6 is going to be putting things into words. And you can check the book for examples of interpreting the independent samples t-test. We will also cover it in class. Okay, so our last one on the list is paired samples t-test, or dependent samples, or matched samples. They all mean the same thing. So the situation that we just went over is when we brought in two independent groups, or different people in the groups. For a paired sample, we're either using the same individuals measured 2 times or we're matching them up. The more common is measured 2 times. Often you'll see people use this in a pre-test, post-test design. So in this case, everything's going to be in terms of the difference score. In other words, we're going to look at an individual score at post-test compared to pre-test, so post-test minus pre-test, and see what the difference is. We're going to do that for each individual in the sample. And then we're going to use that, the difference score that we just created for everybody, and that's actually what we're going to use for the whole test. And once we do that, it just becomes a one sample t-test again, where our population mean is considered to be 0. What the t then looks like is it's the mean of the difference scores minus 0, so that drops out, divided by the standard deviation of the difference scores divided by the square root of n. That means the main thing that we need to do for the paired samples is get a difference score. We're just comparing pre-test and post-test with each other, taking the mean and comparing that to 0. In order to do this, we need a dependent variable on an interval ratio scale again, and we need the IV to define 2 time points. So this is one way that you'll see the data organized. This will be time 1 for person 1 and time 2 for person 1. That means this person started at 8 and went down to 7. This person stayed at 8. This person started at 9 and went to 6. And the other thing is that it's the same individuals measured twice or very matched up individuals measured at different time points. The assumptions are going to be very similar. The independence of data refers to the individuals in the sample, not across time, just is person 1 influencing another person in the sample. Appropriate measurement, same thing, we need 2 interval ratio DVs, 1 for each time point. Normality, the outcome needs to be roughly normal. In that case, it's going to be the difference score should be roughly normal. And homogeneity of variance. The variances of the 2 time points should be roughly the same. So the variance at time 1 should be similar to the variance at time 2. We can check these assumptions, same things. Homogeneity, we're going to use Levine's test to compare this again to see if the variances are roughly the same. Step 2, again, is the null and research hypotheses. Symbolically, this is the mu at time 1 is the same as the mu at time 2. In other words, there's no change from time 1 to time 2. If we're doing a pre-test, post-test design and doing an intervention in between, this means the intervention didn't change anything. So there's no real difference between the means at time 1 and so the mean at time 1, the mean at time 2. And that any differences we see in our sample is due to random chance. So that is the null. And then the research hypothesis is saying that there is a difference and that the difference is real. We would really see it in the population. There really is a difference from time 1 to time 2. Again, step 3 is exactly the same. Go through it quickly. The thing that's different here is now our degrees of freedom is the n of our difference scores. So how many difference scores do we have? -1. So if we had 30 people in our sample, they're measured twice, we'd have 30 difference scores, and that would translate to 29 degrees of freedom. The critical value, again, I just keep using the same one as 2.05. We could define our critical regions as either alpha equals 0.05 or our critical t. Now we can compute the test statistic. For this one, again, everything relies on that difference score, so we're using the mean of the difference score. The hypothesized mean of the difference score, the null hypothesized mean. So what do we think the population mean differences are? The SD of the difference, and the square root of n of how many difference scores you have. Again, this is usually 0. What you're left with is the mean of the difference score divided by the SEM of the difference score. Again, like before, we can compare it to the t critical or look at the p-value. We also, again, are going to use Cohens D, so you're really seeing the similarity across all the different t-tests. We're just using them in slightly different situations, and they give us slightly different things to do, but for the most part, everything's the same. So again, the Cohens D, it's the mean of the difference scores over the SD of the difference scores. The designations are also the same. Last step, interpreting the results. Put your results into words, words that the book provides, that they give good examples. We'll talk about it in class as well. So if you have any questions, please post them to the discussion board before class starts so I can take a look and I can hopefully get to it in class. We'll also be going over the Jamovi examples of using each of these t-tests.